So thanks for the introduction. So I'm Camilo from FZI Karlsruhe. I'm also part of the Human Brain Project SP10 Neurorobotics. And today I want to present the work related to target reaching in robotic. We have a different approach to that. I'm going to explain that later. If you want more details or have questions, I'm on poster 45, so we can discuss it later. Okay, so the first thing is how does, let's say in general terms, motion planning or representation works in classical robotics. So we also saw the presentation from Egidio earlier. There are a lot of important ingredients that are mentioned. The basic stuff is the following. So imagine you have your hand here, you want to go to a different point. What you will do first is to calculate the inverse kinematic, which is like a mathematical solution or an optimization on how your arm should be configured to reach that specific point in space. That's like the first part. Then the second part is you will need to validate that configuration, that it's doable for the kinematic of your robot, so that you can something like this or something different, right? And then the last step is you need to plan a trajectory from whatever you are to that configuration you solve, right? This is a very extensive process, and depending on the kinematic of the robot, then it might become very complex. I mean, we have systems now that have like many actuators that you need to calculate every time, or you have musculoskeletal system, tendon-driven systems that are more complex. For example, this hand only has 24 joints, right? So it becomes very complex to perform the mathematical solutions of this. So we aim at model-less approaches, and for this, what I'm presenting is we don't solve the IK, we don't perform planning, we don't perform validations of the configurations. And instead of that, we use a bioinspired motion representation approach in which we use a hierarchy of motor primitives. And because the motor primitives are defined on the specific robot kinematics, then we don't need to perform the validation because all the configurations within the primitive are valid from the beginning, which is kind of how we work, right? So when a kid starts to move, walk, and move the arm, he will learn how to move his arm. And he will not explore the whole configuration space. He will just explore those configurations that he can perform, right? So it's a restricted problem, and it's more efficient to solve. So how do we model this? I won't go into very deep details on this stuff. We can discuss later in the poster. The idea is the following. So imagine I want to perform this reaching task, extending my arm. So what we do is first we define the motion to have a start and an end, right? And we want to perform a modeling of this motion that is time independent, so that it's not a time sequence, but just a parametric sequence. So we define the start of the motion, whatever motion that is, to be, let's say, 0 in our parameter, and 1 being the end of the motion. And then from that, we perform the mapping to the kinematic. So it looks like this. We have 3 functions, one activation function, which is U or parameter. Then it maps to different functions that could be the primitives. You can define them however you want. And then this gets mapped to the robot kinematics. This is the, let's say, mathematical approach. How does this works or looks like is the following. So if you take different values on your activation parameter, then you will, let's say, travel through your motor primitive, which will result on the following motions, right? So you pick different points here. It's like, imagine you're moving a slider with one hand and then your arm is moving in the other one. This is kind of the operation. So this is just a, let's say, low-level motion representation, right? So what can we do with that? So if we just activate it voluntarily, then you just perform that motion over and over again. There's not much, let's say, intelligence there. So now, the thing with this is that we change the problem. Instead of generating commands in the configuration space of the robot, meaning motor commands for each of the individual motors for every position in space, we're changing the problem on generating the activation parameter, which is the dimension reduction in a very big sense. So if your primitive controls 5 joints, instead of controlling 5 or 10 parameters, you're controlling just 1, right? And the generation of this activation signal could also control the speed. So by just like controlling u on the first derivative of u, or your parameter, then we can control a lot of degrees of freedom. So how do we apply this approach to target reaching? So it's the following. Target reaching is very simply defined. You have a given position where your robot arm is, and then you want to reach a target. And then that's your task. So we redefine this for motor primitives the following way. So the target is represented as a negative feedback signal that we're going to use to trigger the primitives. And we define 3 different motor primitives. 1 for going left and right with the arm, 1 for going up and down, and 1 for going near and far, right? So we have those 3 primitives. We're binding them with the error. And this, this negative signal of the error is just it's a very simple signal. I can explain you more in the poster on the details how we calculate the error. And this is how it operates. So the sphere that you see here represents the target point, the center of the sphere, where we want to go. And the radius of the sphere is the threshold that we use for this experiment. So basically, we're trying to get the TCP within bounds. You see some shaking there, because some of the points that we are generating for this evaluation are like boundary points of the primitive's definition. So it cannot like reach them very properly. But that's what we wanted exactly to show. How did we evaluate this? It's the following way. Among other experiments, these 2 are the most meaningful. The first one is we take the starting position, fixed, and then we sample the whole working space of the arm. So we selected all these points in the working space. Like we sample all the space. You will have to go to a point and come back to 0, go to a point, come back to 0, go to a point, go back to 0, in all the configuration space. And this is a sample of what you will get. So the green is showing you here the target, and then the blue is the position of the TCP. And this is like for, let's say, exhaustive evaluation of that. And you can see that for some points that are, depending on the primitive, for some points that are on the edges of the primitives, we cannot reach them. It's, of course, they're not defined properly in the primitives, but it behaves very good. And the second experiment was that we picked different points as a trajectory in space, and then the arm will not be returning to the starting point. He will just continue traveling on those points. And we got, let's say, the same behavior. You can see here how all the 3 positions of the TCP reach the given target. It starts moving, decreases the error, and then it reaches the target within the threshold. So that's it. So the next steps right now, what we're doing is the following. We're trying to bind this motion with the vision system. So kind of a visual servoing to do basic grasping affordances. So we have some primitives for grasping, and we move the arm around with this approach. And instead of getting the position error to our target, we can get it from the motor configuration of the visual system. And this is what we're working right now. So this is my team. Feel free to contact me. Here's my email. I'm going to be in poster 44. And if you can have questions, thank you very much.